All right, so in this video we are going to be working on some extra practice in writing some of these reactions and nuclear equations, and then kind of figuring out how to write them from certain word problem setups. So we've got the periodic table here. It's going to be good for you to have some periodic table in front of you, whether it's ptable.com or whatever, because it's going to be important to be able to tell what element is being produced based on the atomic number, right? So I'm going to keep referring back to this as we work through these problems. So for example number 1, it says high levels of radioactive radon, and it gives us the symbol, have been found in many homes built on radium-containing rock, leading to the possibility of health hazards. What product results from alpha emission by radon-222? Okay, so there's some story here, right, that doesn't really matter, but the main point is writing an equation. What is the product that results from alpha emission by radon-222? So radon-222 is my starting particle. Radon-222, its atomic number is 86, shown by this one here. I could look up here too. 86 right there. And I've got alpha emission. So radon-222 undergoes alpha emission. That means I know that there's going to be this helium nucleus here, because that's the alpha particle. Right? So now I need to know, the answer to the question is, what's the product? What goes in here? Well, I figure it out by balancing, right? So it's not too tricky once you get the hang of balancing the reactions. So 86, I need, it's going to have the atomic number of something plus 2 equals 86, right? What plus 2 equals 86? It's going to be 84, right? So that these two add up to this one. And then the mass number is going to be 222 minus 4. What plus 4 equals 222? And I think, if I'm doing this off the top of my head right, it is 218. Yeah, I think it's 218. So that's because, again, 4 plus 218 equals 222. Now I go to the periodic table and I look for what element is atomic number 84. So I'm looking up here, 84, 86, 84 is just 2 behind radon, and it's going to be polonium. So I'm going to put PO as the symbol, and so the product is, if I'm answering the question, I would just write out this reaction, but the product that they're asking for is polonium. Okay. So hopefully that's not too bad. Let's go to the next one. Example 2. So strontium 89. So remember, this is the mass number when they give you the isotope there. Strontium 89 is a short-lived beta emitter, often used in the treatment of bone tumors. Write a nuclear equation for the decay, meaning beta decay, because it's a beta emitter, of strontium 89. So I'm starting with strontium 89, I think that's SR, and I have to look, because the problem doesn't tell me what the atomic number is. I know that the mass number is 89, but I need to go up and look, so you could look it up on a periodic table. Strontium is is here. Strontium 89. So strontium has an atomic number of 38. So I'm going to put that in as the atomic number here. Strontium 89 is a beta emitter, and we want to write the equation for that decay. So beta emitter means I have the electron, or the beta particle, as a product. Beta particle, you don't have to write that in, but just to be clear, the beta particle, and so now we figure out what is the other element that's produced. Okay, what's the product? So I have to do the same thing just by balancing, right? So the mass number is 0 on the electron, so I know the mass number here must be 89. And the charge, or kind of where the atomic number is -1. So that means something minus 1 is 38. 39 minus 1 is 38. And again, right, that's just because we need to add these up to equal this. And then I'm going to take this 39 atomic number and scroll up to the periodic table and find which one is atomic number 39. 39 is here. It's yttrium. Symbol is Y. Kind of a weird one. I don't even really... I kind of know how to spell it. It's like YTT. R-I-U-M or something like that. It's one of the weird ones for sure. So yttrium is the product, and this is... They're like, the question was to write the nuclear equation for the decay of strontium 89. So that would be the answer to that question, the whole equation. Okay. So hopefully at this point you kind of feel like you're getting the hang of it. Example 3 is the last example on this page, but then we'll be kind of looking at some on the next page as well. So example 3, what isotope of radium is converted into radon-222 by alpha emission? So now this one, the wording's a little bit different. What isotope of radium is converted into radon-222 by alpha emission? So this one I think we probably actually already looked at a couple times. But the question is saying radium can be converted into radon-222. So that means the radon-222 is the product, and it was formed by alpha emission. So that means the helium particle was produced as well. And it says we're starting out with radium. What isotope of radium was converted into radon-222? So we have radium here. And so for all of those, well, I guess I could fill in the... So radon-222 and the alpha particle are the products. That means I've got 228 up here. Or no, 226. Because I have to add 222 plus 4. It's going to be 226. And then just for completion's sake, I'm going to look up what those atomic numbers are for radon and radium. Radon was 86 and radium is 88. 86 and 88. So that was one I think we probably even looked at in the first video as just an example. But looking at the wording of this problem, what isotope of radium is converted into radon-222 by alpha emission? Got to kind of figure out which particles are the products and which one is the one that you're starting out with as your reactant. Okay, so what isotope of radium is converted? It would be radium-226. Okay, the equation kind of tells you, so I usually just write the equation out, but if I'm really answering the question, I'm going to put in radium-226. Okay, so let's look at the next page, and we might still have to scroll back to our periodic table. So we're looking at some more examples here on this page, and here we've got them set up a little bit differently. So these problems, I took these from a different, they're not from your book. I forgot to just erase this. Those numbers don't mean anything for our class. All right, so nuclear decay. So we want to write nuclear equations for positron emission from the following radioisotopes. Okay. Write nuclear equations for positron emission from the following radioisotopes. It could be good if you want to pause the video and work through these and double check your work with mine. That might be the most helpful thing because you've got what you need to be able to do these. And I'm going to work through them fairly quickly just because we've got what we need. We've set the stage already for being able to do these. So I'm just going to kind of dig in. So write the nuclear equations for positron emission. So we have to remember what that is. That's going to be the positive electron from the following radioisotopes. So I'm going to start with these three particles. And I know that the positron is the product, right? It's the particle that's being emitted in each case. And I need to go to the periodic table and, knowing what I know about balancing, figure out what other particle is formed. So I've got calcium. And because the mass number on this positron is 0, the mass numbers aren't going to change. And the charge on the positron is +1, or kind of that atomic number location is a +1. So our thing +1 needs to equal this number. So it's going to be a 19 + 1 for the first one. It's going to be 53 + 1 for the second one. And it's going to be a 36 + 1 for the third one. So, and then these are what I take back to the periodic table. So I need to figure out what's atomic number 19, what's atomic number 53, and what's atomic number 36. So 19, 53, 36. 19 is potassium. 53, where's 53? 53 is iodine. And 36 is krypton. So it's going to be potassium for the first one. It's going to be iodine for the second one, and krypton for the third one. So I'm going to fill that in. We had potassium, we had iodine, and we had krypton. Okay. So equations for positron emission, this is kind of the key there. And then we just fill in what we have to based on balancing. Okay, so we've got a couple more questions for this video, just trying to get in as much practice as we can. Write the nuclear equations for the formation of each of the following nuclides by beta emission. So we're forming these, so I put them on that side of the arrow because that's what the product is, and it's formed by beta emission. So remember, beta, we've talked a lot about the beta particle, but the beta particle is the electron, and because it's emitted, it's a product, so I can add in the electron in each of these cases. Right? Because they're beta emitters. And now we need to figure out what is the reactant. What is that first atom? What's that first isotope that that is undergoing this beta decay? So again, that just all comes down to balancing. So let's write some of this in. We've got, I'm just adding up, right? I'm adding these two to get the mass number. I'm adding these two to get the atomic number of that first particle. So it's going to be a 3 for the mass number and a 1 for the atomic number, 2 minus 1, which the atomic number 1 we know is hydrogen. The other two we probably won't know. So 210 plus 0 is 210. 83 minus 1 is 82. 20 minus 0 is 20. And 10 minus 1 is 9. So now we're going to take 82 and 9 and figure out what elements have those atomic numbers. So 82 and 9. 82, well, 9 is fluorine, and 82 is lead, Pb. So 82 is lead. Oops, scroll down. 82 is lead, and 9 is fluorine. All right, so we've got this reaction, I guess, or this question, all three reactions. And then we'll move to the last one to wrap this video up, and then we'll talk about half-life in the next one. So the last problem says, write the nuclear equation for the formation of the following radioisotopes by electron capture. Okay, so we're forming these radioisotopes, so it's kind of like the last one where they're one of the products, but these are formed by electron capture. Okay, so electron capture means we have this particle as a reactant. Okay, so I'm going to put that in as a reactant right now for each one. 0 minus 1 electron, 0 minus 1 E, 0 minus 1 E. We're capturing that electron, goes in as a reactant, and now we have to figure out what else is the reactant. Okay, so we've got, so it's just, again, balancing, adding things together. So what plus 0 equals 62? It's got to be 62, right? 110 plus 0 equals 110, and 81 plus 0 equals 81. Now we look at the atomic numbers. So what minus 1 equals 29? 30 minus 1 equals 29. 50 minus 1 equals 49. And 36 minus 1 equals 35. So again, I'm going to take these atomic numbers and go back to the periodic table, because atomic number tells you what the element identity is. So 30, 50, and 36. 30 is zinc, 50 is tin, and 36 again is krypton. So zinc, tin, krypton. Scroll back down to this problem, and we get, oh, I didn't leave enough room. Okay, let's erase these little guys. I got ahead of myself, kind of. Okay. Zinc, tin, and krypton. Okay. So those would be our nuclear equations for the formation of these radioisotopes by electron capture, the electrons going in as the reactant. Okay? So I'm going to stop this video at this point, and we are going to wrap up this chapter and the class by talking about radioactive half-life.